Hi everyone, welcome to this quick and focused session on relational algebra in DBMS. If you have worked with SQL before, you already know how to query a database. But what happens behind the scenes? What is where relational algebra becomes in? It is the theoretical backbone of SQL and it is used to describe how queries are actually executed in a relational database. This presentation will walk you through the key operations of relational algebra like selection, projection, union and more along with examples and outputs so you can clearly understand how each operation works. So why is this important? Because relational algebra provides a mathematical step-by-step way to retrieve data. It is used in query optimization, database compilers, and it is an essential concept for any computer science or data engineering student. Stick with me as we break down each operation one by one. Let's begin by answering the first big question. What is relational algebra? Coming up next in slide 2. What is relational algebra? It is a procedural query language used in relational databases. That means instead of just saying what data we want, like in SQL, we describe how to get it step by step. Relational algebra works on relations, which are simply tables. It uses a set of operations like filtering, combining, or selecting data to produce new tables as output. One key reason relational algebra is so important is that it is the foundation of SQL. Every SQL query you write is internally converted into relational algebra expressions before being optimized and executed. It is also used in query optimization, helping databases decide the best way to fetch your data quickly and efficiently. And for those working on database engineers or quickly planners, relational algebra is an essential tool. To summarize, it's procedural, it operates on tables, means relations. It forms the base of SQL. It is key to understanding how database works internally. In the next slide, we will explore what a relation actually look like, its structure, schema, and tuples. Let's move on. Basic structure of a relation. Before we dive into relational algebra operations, let's quickly understand what a relation is in databases. A relation is just a table made up of rows and columns in database terms. Columns are called attributes, rows are called tuples. The structure or layout of a table is called the schema. For example, consider the relation student, ID, name, age. This means we have a table with three attributes ID, name, and age. Each row or tuple in the table represents a single student's data. Why is this important? Because every relational algebra operation works on these tables, taking one or more relations as input and returning another relation as output. Understanding schema and tuples help you apply relations correctly, like knowing what columns you can project or what conditions you can filter. Coming up next, let's jump into the core operation of relational algebra, starting with selection. Types of relational algebra operations. Relational algebra provides a set of powerful operations to manipulate and retrieve data from tables. The major operations are selection, filter row based on a condition. Projection, it is denoted by pi symbol. Pick specific column from a table. Union, combine data from two tables. Set difference, find what's in one table but not the other. Cartesian product, combine every row of one table with every row of another. Rename, rename a table or its columns. Join operations, combine related data from different tables. Think of these as a building blocks. Complex queries are just a combination of these operations. Next, we will break down each one starting with the selection operation. Selection. Let's start with the selection operation denoted by the Greek letter sigma. Selection filters row based on a given condition. It works like a where clause in SQL. Syntax: sigma condition in that bracket relation. Example: suppose we have a table student with columns ID, name and age. If you want students older than 20, we write sigma age greater than 20 in the bracket student. Simple input table: ID, name, age in ID row 1, 2. Names: Alice, Bob, age 21, 19. Output: ID, name, age 1, Alice 21. As we can see, only Alice is selected because she meets the condition. Next up, we will look at the projection, which focuses on columns instead of rows. Projection. Now let's talk about projection, represented by the Greek letter pi. Projection is used to select specific columns from a table. Syntax: pi column names in bracket relation. Example: from our student table, if we want just the names and ages, we write pi name, comma age in bracket student. Input table: ID 1, 2, name Alice, Bob, age 21, 19. Output: name Alice, Bob, age 21, 19. Notice that the ID column is excluded. One important thing: projection automatically removes duplicates because relational algebra treats results as sets. Up next, we will see how to combine data using the union operation. Union. The union operation, denoted by U symbol, combines rows from two relations into one. Syntax: R, U symbol, S. But there is a rule. Both relations must be union compatible, meaning they have the same number of columns and matching data types. Example: say we have two student tables. Student 1, ID 1, 2, name Alice, Bob. Student 2, ID 3, 4, name Carol, Dave. Student 1 union student 2 results in ID 1, 2, 3, 4, name Alice, Bob, Carol, Dave. Just like in set theory, duplicates are removed. Coming up next is set difference, where we subtract one table from set difference. The set difference operation, denoted by minus, finds rows that are in one relation but not in another. Syntax: R minus S. Again, both relations must be union compatible. Example: students 1, ID 1, 2, name Alice, Bob. Students 2, ID 3, 2, name Carol, Bob. Students 1 minus students 2 gives ID 1, name Alice. Bob exists in both, so he is removed. Only Alice remains. This operation is useful when finding exclusions, like users who signed up but didn't register for a course. Next, we will explore the Cartesian product, which pairs every row of one table with every row of another. Cartesian product. The Cartesian product, denoted by into symbol, returns all possible combinations of rows from two relations. R multiplication symbol S. If relation R has m rows and S has n rows, The result will have m into n rows. Example, students ID 1, 2, name Alice, Bob, courses code 1, C1, C2. The results of students into courses ID 1, 2, 1, 1, 2, 2. Name Alice, Alice, Bob, Bob. Code C1, C2, C1, C2. This operation is often used as a step in join operations, where we later apply conditions to filter relevant combinations. Let's wrap it up now with a quick conclusion. Rename. Let's now look at the rename operation, denoted by the Greek letter rho. Rename is a simple but powerful operation. It lets you assign a new name to relation or its attributes. This is especially useful when working with complex queries or when joining a relation with itself. Syntax: row, new name, in brackets, old relation, or row, new name, in that bracket, a1, comma, a2, comma, and so on, an, and bracket relation. For example, say we have a relation student, ID, name, age. If you want to rename it as we write row s in bracket student. We can also rename attributes row s, s ID, s name, s age in the bracket student. Rename doesn't change the data, just the table labels, but it helps avoid confusion and conflicts in queries. Up next, we will dive into join operations, which combine data from multiple relations. Join operations overview. Join operations are among the most important in relational algebra. They allow us to combine related data from two or more relations. A join is basically a Cartesian product followed by selection. There are several types of joins: theta join, equijoin, natural join, outer joins, left outer join, right outer join, full advanced. Let's focus on the first three, which are most commonly used. Joins are vital when dealing with normalized databases, where data is split across tables to reduce redundancy. Let's begin with the theta joint. Conclusion. Let's quickly summarize what we have learned. Relational algebra is a procedural language for querying databases. It works with relations or tables and returns new relations as output. We explored key operations: selection, filters rows; projection, choose columns; union, combines rows from two tables; set difference, find rows in one but not the other; Cartesian product, combine every row from two tables. These operations are the building blocks behind SQL queries and are crucial for optimization and database design. With examples and outputs, you now understand how data is processed internally in a relational database. Thanks for watching. Don't forget to like, share, and subscribe for more DBMS concepts explained clearly.